Alright, so far we've discussed the activation functions, and in this tutorial we begin to talk about the weight initialization. Why is it important to learn about weight initialization? Well, weight initialization in the neural networks matter when it comes to the performance of the neural network, both in terms of accuracy as well as its convergence. So a neural network initialized with appropriate weights would converge faster, would save you on compute, plus it'll give you better results. And that's why it becomes important to know about weight initialization. But there are certain common mistakes that people tend to make when they're experimenting with weights, and we'll talk about those first. Then we'll talk about the right technique to initialize the weights. To begin with, let's look at a simple neural network. We have an input layer which has 2 neurons. We have a hidden layer which has just 3 neurons, and we have an output layer. This is a usual fully connected neural network where the inputs get aggregated at the hidden neurons through the weighted sums. And let's say this aggregation is A11, A12, and A13. The hidden neurons have one and the same common activation function. Let's say that's G in this case. It could be any activation function like ReLU, tanh, sigmoid. But let's just say we're saying in general right now it's represented by G. Then we have these connections between the hidden neurons and the output neuron. The weighted sum of the outputs from the hidden neurons gets aggregated at the output neuron, and that's denoted by Z. Finally, that undergoes an activation function F, and it gives an output Y hat, which is our prediction. So let's talk about a specific case where we are assuming that all these weights here between the input layer and the hidden layer are one and the same, and all these weights from the hidden layer to the output layer are one and the same. Please note, for our example, we have considered these set of weights as W1s and these set of weights as W2s. Now let's try to understand how this aggregation would work as we receive the inputs and do a weighted sum. So let's look at it closely. This A11 is supposed to be W1x1, the input that's attached to this connection, and it would add W1x2. Why W1? Because these are all one and the same weights. This A12 is again W1x1 because this connection is again weighing W1, plus W1x2 because this again is W1. And similarly, you can imagine this A13 would again be one and the same. So all these aggregations now, because we've chosen the same weights, are one and the same. And let's say we denote it by a general symbol A. Now these aggregations are supposed to be given as input to an activation function. And we know the activation function within a layer has to be one and the same in a neural network. Let's say it's sigmoid or tanh or anything for that matter, it's receiving one and the same input. This is a standard function. If it receives one and the same input, it's going to give a standard output. And let's say the output in this case could have been H11, H12, H13. But in our particular case, all these would again be equal. Because they receive the same input, they'll give the same output. And let's say that's represented by H. Now, once again, we will be doing an aggregation of all these outputs, and we will be putting it here as Z. So in a general scenario, that would have been W2, because all these weights are W2s, W2H11 plus W2H12 plus W2H13. But we have a special case. All these are W2Hs, because H11 is H, H12 is H, and H13 is H. So finally putting the value of H here for all these three representations will get Z as 3 times W2H. Now imagine the Z going as an input to a sigmoid for a binary classification problem. This Y hat is going to be 1 over 1 plus e raised to the power negative Z, where Z is 3 times W2H. So this piece that we discussed just so far is the feed-forward neural network. We started from the inputs and we have come to the prediction stage. But now we will evaluate the loss. We'll compare this Y hat or the predicted value with the actual value. So here comes the loss. And loss could be a specific function, but let's say in our case, we are saying it will be proportional to the difference between Y and Y hat. How far we are from the actual label is what we are looking at. And we eventually want to figure out how do we go about updating these weights. As we know, in a neural network, these weights and biases essentially are responsible for training of a neural network. For our example, we've not considered the bias term. We are assuming that to be 0, just for simplicity of calculations. But at least we should talk about how these weights will be updated. Now let's look at the expression for weight update. So W2 new would be W2 old minus eta, or the learning rate, which is a hyperparameter, times dou L by dou W2. Now we need to totally concentrate on this expression. It talks about how much would the loss change as we change W2. Going by the chain rule, we can write dou L by dou W2 in this form on the right. So we are saying the loss depends on y hat, which is very clear. This y hat depends on the previous aggregation, which is dou z. And this previous aggregation essentially depends on the previous weights. If we know these three derivatives, we can find out dou L by dou W2. Now the point here is that this dou z by dou W2 can be found out easily if we know what is z. And we saw that earlier, that z is simply 3 times W2h. Now, if we take a derivative of 3W2h with respect to W2, it'll be simply 3h, because this 3 and h would act as constants. Derivative of W2 with respect to W2 would be 1. But the point is, would there be any difference in these three connections as we move back? Because this quantity that we are computing is going to be one and the same for all the three connections. So the new weights that we will update after fitting the dou L by dou W2 here will all still be one and the same, because there is no way that we can differentiate between these three connections, as the value of the loss with respect to W2 is one and the same for these three connections. Now let's move a step backwards and try to figure out how would we update these weights W1s. So again, the expression would be one and the same, but you can imagine as we are tracing it backwards, we'll have more derivatives to look at. So it'll be given by something like this. So loss depends on y hat depends on z depends on h depends on the previous aggregations, and previous aggregation a's depend on W1s. That's what we have written here. Now here, once again, we know this value of a is one and the same, a11, a12, a13, which was W1x1 plus W1x2. If we take a derivative of this with respect to W1, we will get x1 plus x2. Once again, for any of these weights, we will not be able to get a different update. This value of dou L by dou W1 is going to be one and the same even if we keep on putting all the values here. So these weights will remain equal. They may not be the same as W1s because they'll be updated, but the weights will remain one and the same as the point. And this is called a symmetry breaking problem. We are not able to break the symmetry. And why is it important to break the symmetry? It's important to break the symmetry because we originally discussed that weights kind of indicate the importance of an input to a neuron, and so on from the hidden layer to the output. But in our case, right now, the network that we're looking at, there is no difference between any hidden neuron. They are doing one and the same thing. They receive the same exact input as aggregation. They give the same exact output as the activation. And as we move back, again, the inputs and outputs for these hidden neurons remain one and the same. So do we really need multiple hidden neurons, or we can manage with just one is the question that arises. Let's look at the network in isolation, and we've just placed these A11, A12 values with A's and H11, H12 values with H's. If you look at this network, we went through these 6 connections first, then we went through these 3 connections between the hidden layer and the output layer, and the aggregated value of Z was 3W2H. Can we replace this with an equivalent network which is like this? So instead of looking at 3 different neurons, we are looking at just one neuron. All we've done is that instead of looking at these weights as W2s coming through 3 connections, we've made it just one connection which weighs 3W2. Now, while we took a simple example of 3 neurons, you can imagine even if you had 100 neurons here, those 100 neurons could be reduced down to just one single neuron. So the point is, if we choose to initialize the weights as all equals, then we can reduce our entire hidden layer to one single neuron. So fine, we can reduce an entire hidden layer to a single neuron. What's wrong in that? Well, what's wrong is the fact that we came to the idea of multiple neurons in a hidden layer to be able to solve complex problems, the nonlinear problems. If we reduce that down to a single neuron, we will only be able to solve linear problems once again. And then probably we don't even need neural networks. We can solve such problems using linear or logistic regression as well. So the main takeaway is that we should not initialize the weights as equals.